Good. Oops. Yes. Okay. So, so uh, hi everyone. Good afternoon to those who have afternoon. It's a pleasure to, at least remotely, for me give this presentation. I should thank the organizers and thanks to Matthias for the introduction. So this is a part of a bigger project in collaboration with a couple of applied mathematicians and statisticians, Daniel Appelo, Virginia Tech, Gabriel Huerta in San Diego National Lab, and Anders Petersson in Lawrence Livermore National Lab, and my PhD student Chase Hodges-Haleman at UNM. So let's see. Okay, so I will give a three-part presentation. First, I will talk about this like beautiful chandelier-like structure, which we call quantum computer. And then I move on to giving a very short overview on optimal transport, the type of measures that I will be using, and then the Bayesian framework or the generalized Bayesian framework that I do uncertainty quantification within. So just please feel free to interrupt if there is any questions that would help. That would be a big help, not only to you, but also to me. And so, okay, I mean, classical computers which work on bits to represent information, a quantum computer works on qubits. And then a quantum computer utilizes two tools, which we call superposition and entanglement. And this enables a quantum computer to do powerful computations. Okay, so what does superposition mean? A single qubit can be either in like fundamental states, a state 0 and a state 1. So this is the Dirac bracket notation, and it's nothing but just a vector with 1, 0, and then a vector with 0, 1. These are the two fundamental or pure states. But a qubit can also at the same time be in both states. And an arbitrary state denoted by psi can be written as a linear combination of the two states, and the coefficients are complex valued. Okay. The state of a quantum computer is decided on probability. This means it would be, I mean, in the end of computations, when we do measurements, the state is either in fundamental state 0 or fundamental state 1, but with corresponding probabilities. And those probabilities would be the modulus of the coefficient of fundamental state 0 squared. This would be probability of the state being at the state 0. And then the square of the modulus of B, which would be the probability of the state being in fundamental state 1. Okay, so in the end of measurements, in the end of computations, when we measure the state would either be in fundamental state 0 or from fundamental state 1, and with corresponding probabilities. Okay, so what this superposition does is that it enables the system to be represented in a two-dimensional vector space. And you just paired this with classical computer is represented only by two states. So this is much larger. One can do much more powerful computations in a two-dimensional vector space rather than just using two specific vectors. When we can, of course, use more qubits, like if we have q qubits, then we get entanglement. What it does is that It actually spans the space to a 2 to power q dimensional vector space compared to just 2 to power q states. For example, when q is 2, the standard basis for the fundamental states can be formed by the tensor product of the fundamental spaces of qubits, single qubits, right? So if this would form 4 fundamental states, but in a quantum computer, the state can be constructed by superposition or a linear combination of all these four vectors, four basis vectors, and then this would amount to a 2 to power q dimensional vector space. So you can, sorry, just to give an idea, if you think of a 2-dimensional function, f of xy, it's like a classical computer would just consider functions of this form, which can be factored into like function of x times a function of y, while a quantum computer can handle much more general functions of x and y. Okay, so we would, of course, need quantum gates similar to logical gates in a classical computer. And this needs to be understood in the sense of quantum states. Evolution of a quantum state from a state psi to let's say, a state psi prime is achieved via a unitary operator u. Okay, so this means psi prime would be given by multiplying the current state psi from left by a unitary matrix U. And this matrix is what we call a quantum gate. Okay, we need to design, if we want to achieve some state psi prime, some computations, then we need to design, by designing the gate, we mean we want to obtain this unitary matrix. Examples include, for example, in a case of 1 qubit, a 0-1 swap. This is given by this unitary matrix, which what it does, it just flips the fundamental state 0 and fundamental state 1. And it's denoted by, in a graphic way, which we call a quantum circuit language. It's represented by X or like this. In the case of two qubit system, for example, the controlled knot is given by this unitary matrix, and what it does is just it flips the states in the second qubit. Okay. In graphic representation of a gate would be like this. This is called a wire. It's like a horizontal line. We put the gate inside a box. To the left, we have the current state, or the state that we initiate the computations with, and then the output would be this matrix multiplication, which would be the gate application. And then when we have multiple qubits, each wire would be assigned to each individual qubit. And then we have a sequence of gates applied either using single qubits or 2-qubit gates. And then in the end of the day, we do measurements. Okay, this is just the quantum circuit language. We write algorithms in this way. How to implement the gates? They are done through applying controls, which take the form of microwave or laser pulses. Okay, the way that we obtain these pulses is through an optimal control problem, which is driven by some dynamical systems. For example, they could be governed by Schrödinger equation, where H is the Hamiltonian. It's usually split into the system Hamiltonian, which takes the parameters of the quantum system, like transition frequencies, and then the control Hamiltonian, which actually is the part where we apply these gate pulses. or control pulse. And then, so the idea is to, I mean, with a target gate, we compute or we obtain a pulse through solving an optimal control problem, and then we give this pulse into the control Hamiltonian. We also need to know the parameters of the quantum system. We give it to the system Hamiltonian, and then we run the Schrödinger equation to over time to find a later state. Okay, this is how the gate is applied. Alternatively, one can do more complex dynamical systems like Lindblad's master equation, which is given in terms of a density matrix. And this would, the difference with Schrödinger equation is that Lindblad equation would consider also the coherence, which is interaction of the interaction of the quantum computer with the outside environment. I mean, the heat, the temperature change in temperature, vibrations, and so forth. Okay, so the procedure summary is one can split this into two parts, the software and hardware. The software is, first we would need a quantum algorithm. And I think if I'm not mistaken, this morning and yesterday morning, hopefully you have seen some quantum algorithms. But in any case, we need some quantum algorithms that would work on quantum computers. Then we need to implement this using this quantum series, which is a sequence of single and two qubit gates applied on qubits. And then it also involves the optimal control, the quantum optimal control that would model or implement the gates through some microwave pulses. And then it's in the hardware, after we have set up, we have this setup, then in the hardware level, one needs to manipulate the qubits, apply this, the microwave pulses to the quantum computer, do some preparation. We need to prepare states, different qubits in different states, and then we need to do measurements. So all this will happen in hardware, and then since the quantum state is decided on probabilities, one needs to repeat this many times and then collect statistics, and those would be the ultimate outputs of the computations. The quantum algorithms, so what is good about this is that in theory, a quantum computer, quantum algorithm has the potential to provide exponential speed up compared to classical computing. For example, if you think of fast Fourier transform, which is of order of n log n, a quantum Fourier transform can do computations in order of log squared n. So this is like exponential speed up in computations. This is just theory, right? In practice, the universe plays against us. What the universe does, and by universe, I mean the surrounding environment, what it does is that it tries to change the state of the qubits. And if you recall, the state of a qubit is decided on probabilities. So the surrounding environment tries to change those probabilities. Suppose that we have a qubit with probability 51% and 49%, right? 51% for the state to be in fundamental state 0, and 49% for the state to be in fundamental state 1. Now assume that we have some thermal noise or some vibration or some magnetism, electromagnetism or light, or some cosmic waves that would change this to, instead of 51%, 49%, we would get 49%, 51%. Then this would impact computations, right? So in practice, physical realization of a qubit is quite tricky. There are, of course, different ways that physicists are working on, like ion trap, neutral atoms, or superconducting transmons. But all those are prone to uncertainty, and we also have the problem of scalability. Uncertainty can be split in two parts: experimental uncertainty, which is due to interaction with the environment. It's due to a state preparation and measurement errors. So we need to prepare the quantum computer or the qubit in some state, either a state 0 and a state 1. And there are always, this is not a very easy task. Sometimes we think that we have prepared the qubit in a state 0 while it's in a state 1. Also, we need amplifiers that to amplify the weak pulses, weak signals of the device. And there is variability in amplification factor of those amplifiers. So there is a list of sources of experimental uncertainty, which is hard to reduce. For example, they put this the quantum computers, which you see here in the top right panel. They put it in a refrigerator just to keep the temperature at very close to the absolute zero, about 10 or 15 millikelvin, to reduce the impact of thermal noise, for example. But still, it's very hard to control different sources of uncertainty. It's there and it will impact computations. And we also have model form uncertainty, and this is due to the inadequacy of the available dynamical models. For example, Schrödinger and Lindblad equations are not perfect models, and that would introduce model form uncertainty. And then scalability is due to, to make powerful computations, we would need many qubits, and then the size of the system would grow exponentially with the number of qubits. That would bring scalability issues, challenges with computations, right? It's much harder to compute systems which are super large. So today I will I will focus on uncertainty. I will not touch on a scalability issue, but so hopefully we can, of course, this is not a very bad news for researchers like me, because this means there is room to do research. And it's a perfect, it's a very interesting problem. It has a very complex uncertainty, and that makes it interesting to do uncertainty quantification. Okay, so a little bit about quantum measurements. We have a couple of different experimental protocols for quantum computers. A typical one is Ramsey experiments. So what they do is that first they apply some pulses, which they call pi pulses, to prepare the system, the qubits in some states. And then they also apply a pi half pulse so that they bring the qubits into superposition state. And then they let the computer run or evolve in time for some time that they call dark time without applying any pulses. And then in the end of that, they do measurements. And they do that for each dark time. They do it like 1,000 or 2,000 times. Each time is called a shot. So they do 1,000 shots, and then they compute, they find out which state the qubit is in, and then they compute the probabilities. So what you see here is the probabilities or the population plot of the qubit in different states. Here I have one single qubit. It's actually a qubit. It contains, I mean, the qubit doesn't have to be to follow a binary state. It could have, for example, my qubit here is a state 0, consists of a state 0, a state 1, and a state 2. So this is a 3-state qubit. And then what you see here is the probability of the state being in one of these 3 states at any fixed dark time. And I have about 1,000 dark times here. Okay, and if you just could simply observe the complex structure of noise, especially in these flipping regions, where yeah, the noise is quite large, and it's like it's so this just to represent or to motivate the complex structure of the noise in quantum computers. Quantum characterization. So um, if so again, the Hamiltonian in Schrödinger or Lindblad master equations consists of 2 parts. The system Hamiltonian has the system parameters denoted by alpha, and the control Hamiltonian has control parameters, which these are the pulses or the gate pulses, right? So to find the gate pulses, one needs accurate information about the system parameters. So finding or inferring system parameters alpha through measurements, through quantum measurements, is called quantum characterization. So in UQ community, we would call it like inference, or this is just Bayesian inversion, to infer parameters, system parameters using the data. And then this would play a very important role in finding robust gates. Okay, so quantum characterization is a crucial step in finding quantum gates. And it involves collection of quantum data and then a model fit to the data using like a dynamical system model. Bayesian-type quantum characterizations are attractive because they account for the uncertainty in quantum computers, and they would allow risk-neutral optimal control, meaning that we, instead of minimizing the gate infidelity at just one fixed set of parameters, we minimize, for example, the expectation of the gate infidelity, where the expectation is taken against the distribution of system parameters. Okay, and that would enable, that would lead to more robust gates, robust in the sense that they would not change if the computer, the quantum computer, changes due to interaction with the environment. Okay, so this is a part of the project we do. It involves, it starts with the quantum computer collecting data, and then we do some Bayesian or Bayesian-type characterization that I explain shortly. And then this would lead to posteriors for device parameters. And then we do optimal transport, risk-neutral optimal control. And then we find the pulses that would implement the gates. And then we give these pulses to the quantum computer to do the computations that they are supposed to do. And this is just a motivating example what a careful uncertainty quantification can do. This is what I'm showing here is the gate infidelity. For a simple gate, it's a 0-2 swap. This means that it just swaps or changes a state 0 and a state 2 of my qubit, and versus perturbations in the Hamiltonian. So what we observe here, what we see here, the blue curve is the traditional control. This is not using, this is just a deterministic fitting. No uncertainty has been accounted for here. And you see the gradation of the infidelity of the gate infidelity as the Hamiltonian perturbation increases, right? So, and then the green one is using Bayesian standard Bayesian inversion, like using Gaussian likelihood, and then doing risk neutral optimal control. So this would be, this improves this, I mean, terrible behavior degradation quite a bit. And then the red one is what we are doing using optimal transport. And that's, I mean, this is remarkably much better in the sense of robustness. So the infidelity remains steady as with the changes in the Hamiltonian. So this is a motivating example that what uncertainty quantification can do to perform robust computations with quantum computers. Okay, so before I start, move on to the second part, if there is any question, please let me know.
Seems you can move on.
Perfect.
Mohammad, thank you.
So so I just give a very quick overview. This is a work I did in like 2 years ago, just to make sure that we are all on the same ship. It's a fast or a low rank optimal transport measure that would be a perfect fit to the case of to our quantum computing problems. Okay, so let me give a very brief overview of discrete optimal transport. Suppose we have two feature spaces, X and Y. X is the source space, Y is the target space. And then they are endowed with a metric, or which we call ground metric, D. This is, for example, this could be just the L2 norm. And then we consider two discrete probability measures, Fn and Gn, supported on X and Y. Okay, so this would be our source probability measure, and G would be our target probability measures. Delta here is the Dirac point mass measure, and then F and G's are the weights which form two probability vectors, meaning that they are positive, that they sum to 1. Okay, so the idea is in optimal transport, we want you can think of the source as just a pile of sand, and then a hole, the target as a whole, and then we want to move this in an optimal way. For this, we consider a transport plan, which is basically a doubly stochastic matrix P. Each element of this matrix represents the amount of mass to be transported from point xi to point yj, and such that the row sum is the probability vector f, and then the column sum is the probability vector g. Okay, of course, there are infinitely many possibilities for forming this transport plan, but we want the optimal transport plan. For that, we introduce a transport cost, using a cost function. The cost function is defined in terms of the ground metric that we have. So the ground metric to some power p. As an example, if the ground matrix is L2 norm, then a typical P would be 2, right? And that would introduce a cost matrix. Now, each component of this cost matrix represents the cost of transporting 1 unit of mass from xi to yj. And obviously, the total cost of transportation would be given by the Frobenius inner product of the transport plan and the cost matrix, right? This is the Hadamard product. And we want to minimize it. We want to find the transport plan that minimizes this transport cost. So this T would be the optimal transport cost, right? And this is called the Kontrovich optimal transport problem. So for our purposes, this induces a very useful metric, which we call Wasserstein distance, and that's nothing but the pth root of the optimal transport cost. Okay, one can show that this is a metric, and it has nice geometric properties like convexity, and it's one of the most popular type of Wasserstein distance is the quadratic Wasserstein distance, which is obtained by just when we take the ground distance to be just the L2 norm. Okay. So despite the advantages that Wasserstein distance has, it's unfortunately computationally very expensive in multiple dimensions. In one dimensions, we have closed form formulas and it's near linear. But in more than one dimensions, it's, in general, it's cubic. So the cost of computing Wasserstein distance, for example, in 2 dimensions, is in general cubic. In some very specific cases, one can do subcubic computations, but in general, it's cubic. And that makes it intractable when the number of data points is of moderate size. Okay, the other issue is that the data need to be probability vectors. They need to be positive and they need to have unit mass, right? And this makes it not directly applicable to sign data, like the data that we have, or the data that don't have a unit mass, like the typical type of data that we have in quantum computing. Okay, so there is a way to speed up computations, introducing a slightly different optimal transport distance. And then I will address the second issue by data normalization. Okay, so to find the fast or to derive the fast approach, which would amount to this low rank optimal transport measure, the first step is to add an entropic regularized penalty term. So this H of P is the entropy, and then we multiply it by a small number, and then we add it to the optimal transport cost. And then we define it as a regularized optimal transport cost, T sub epsilon. And then based on this, one can define a new measure, which is referred to as debiased Sinkhorn divergence, denoted by S. And this is, it just takes the regularized optimal cost, but it also does a simple kernel trick so that it makes it positive definite. When f is equal to g, of course, T epsilon would not be 0 because we are adding this penalty term, but this simple trick makes it positive definite, right? So when f and g are equal, then the debiased Sinkhorn divergence would be 0. It's shown that this the divergence is symmetric, positive, definite, and smooth. And it also has nice convexity properties. But the reason that it's called a divergence and not a metric is that it fails to satisfy triangle inequality. It's a conjecture that I have not been able to prove yet. The conjecture is that it satisfies a weaker triangle inequality, with K being a bounded number larger than or equal to 1. I have, or one of my students performed extensive numerical experiments, and we couldn't find the best or the largest K that we obtained was less than 1.1. For that reason, I would um, I would call this divergence a quasi-distance. And then for short, I just call it Sinkhorn distance. Just keep in mind that this does not satisfy the triangle inequality, but we conjecture that it does satisfy a weak triangle inequality. So this is the measure, the measure that can be computed very efficiently. And the technique is pretty simple. It starts with the Sinkhorn algorithm and as follows. So the optimal or the regularized optimal transport cost takes a simple structure. It's the product of three matrices. The Q matrix is a kernel matrix induced by the cost matrix C. And then we have two positive diagonal matrices U and V. So of course we have Q, right? Because we have C. The only thing we need to compute are these positive vectors U and V. And then because of this simple structure, we can just use the marginal conditions. Recall that we want the row sum of P to be F and the column sum to be G. So this gives us two equations, and then we can use plugging this simple structure into these two equations, and then we do fixed point iteration. So after k iterations, we can compute the optimal cost. And then we need to do 3 runs of this to find the debiased Sinkhorn distance. So the computational complexity of this is the number of iterations times n squared. N squared comes from this matrix vector multiplication, right? And k is the number of times the number of iterations. And it can be shown that the number of iterations is proportional, logarithmically proportional to n. In practice, one converges very fast. I mean, in like 3 or 4 iterations is enough to achieve a small error. The error is the difference between the Sinkhorn distance and the Wasserstein distance. This error does not have to be very small. I mean, if we want to use this Sinkhorn distance as an approximation for Wasserstein distance, then it might make sense for the error to be small. But this distance is already a good distance. It is a distance by its own. The goal is not to approximate the Wasserstein distance. And for that reason, epsilon tol, or the tolerance, can be chosen large, for example, of order of 0.1. And so the major cost of this computing the Sinkhorn distance is n squared. This is already much smaller than the cubic cost of Wasserstein distance, but one can do even better. One can make this near linear cost, noting that the major bottleneck, this n squared, comes from the matrix vector multiplication, and the matrix is a super nice kernel matrix. So one can use the Kronecker structure and the asymptotic, a smooth structure of the kernel. One can utilize these nice properties to speed up computations. The Kronecker product structure comes from this additive representation of the cost, and and then the smoothness comes from this exponential decay. So it comes from the this property. The farther the 2 points are, the smaller the derivative of the kernel. And this means as we uh, move on, uh, as we get farther away from the main diagonal, the kernel becomes smoother and smoother. And this enables us to use the hierarchical matrix approach. And we using like a quadtree splitting or partitioning, we partition the matrix into different blocks. The blocks away from diagonal are large and they are smooth. The kernel is smooth on these large blocks, and they can be, we can do low rank approximation. So this amounts to a hierarchically low rank approximation of the kernel, and then a careful error complexity analysis would be performed to show that the cost of computing Sinkhorn distance is near linear. Data normalization, one possibility is to just measure the distance between the positive parts and the negative parts of the signal, and then we add up them together. The problem with this approach is that we lose a smoothness, and that's not good for example, solving inverse problems like gradient-based optimization techniques, which a smoothness would be um, something that we require. So another approach is to do data normalization using like a smooth and one-to-one function denoted by sigma. We can project the signal, the sine signal, into positive signals with unit mass. A, a, a useful scaling or normalization strategy is soft plus. We multiply the signal by some scaling factor, delta, which would serve as a hyperparameter. We exponentiate, we add 1, and then we take logarithm. This is the soft plus scaling. And then we apply, after we normalize the signal, we apply the Sinkhorn distance. And that would define the normalized Sinkhorn distance. And one can show that it has similar nice properties as the Sinkhorn distance. It's symmetric, positive, definite. It's smooth. And it also convex for if this scaling parameter is larger than is large enough. So just let me show you one simple example to highlight the nice property, or in terms of convexity of this Sinkhorn distance. So here I have a signal f, which is formed by like 3 bumps. And then I have 2 types of them. I have like wide signals and I have narrow signals. So the narrow signal represents high frequency waves, for example, when the wavelength is small. And then the simulated data G is obtained by a shifted version of the observed data F, right? And then the phase parameter or the shift parameter changes between, let's say, in some range, between negative 0.3 and 0.3, okay? So what I'm plotting here is the distance, different types of distances with respect to the parameter, the shift parameter. The black is the L2 distance, which is oscillatory, so it has local minima. The Wasserstein distance is red. It's pretty convex, but then the best convexity property is like the Sinkhorn distance, the blue one. Okay, this is for the white signal, and then I'm using a soft plus normalization with just a small delta, which is 0.5. When I move to narrow signals, L2 behaves not good as before, but then the red one, the Wasserstein distance, starts to lose convexity, while the Sinkhorn distance preserves its convexity. So this is a result of the smoothness, the entropy term that we add to the Wasserstein distance that would help with convexity. And in particular, it makes it pretty robust, pretty stable against the changes in the hyperparameter delta. So in other words, while Wasserstein distance is more sensitive to this normalization strategy, the Sinkhorn distance remains, I mean, behaves more stably. It's more stable against changes in the hyperparameter. This is a more complex example. We have a more complex signal, and then similar things are observed. The blue is the debiased Sinkhorn. The red is Wasserstein distance. This is with delta 0.5. Of course, if we increase delta, for example, to 3, we can make the Wasserstein distance behave like with a better convexity property. But the problem is that when we increase delta, then you are making large changes to the data. And so let me skip this. This was a toy problem. I applied this to functional MRI images, just to which are 4-dimensional images. So for this image in 4 dimension, so the number of data points is like crazy, and then Wasserstein distance, the cost of computing Wasserstein distance would be this number to power 3, which is not tractable many times, of course. So this was just an example. I applied Sinkhorn distance to find the average of, let's say, 20 images of 20 different individuals. Okay, so any questions? I believe I have about 10 minutes.
Yes. Yeah, please. Yeah, we have a question here. Hold on.
Yeah, hello, Alexander here. So
Hi, Alex.
on slide number 17, just short question, matrices P and C, how do you know that they are not uncertain? Can they be uncertain?
C.
So can, yes, cost, for example.
I mean, for me, it's
So they
it's
determine.
so for me, it's fixed, right? So that I mean, if you go back to the discrete probability measures supported on the points, I assume that these points are fixed.
Okay.
So they come from like it's like here. I assume that the dark times are fixed. So this is
Okay, I see.
the evolution time, the time that the quantum system runs, and we have a pretty good control on that. Let's say we decide to, after 10 microsec, we decide to compute, to make measurements.
Okay, I see, yes. And next
So,
question on slides 19. Actually, here you see in the middle you have a Kronecker product of matrices. Actually, you can combine tensors with hierarchical matrices, so you can approximate every single factor in tensor decomposition by just was an idea. But you approximated here global matrix, yes? Global matrix Q.
No, you are right. I do approximate each individual matrix by a hierarchical matrix.
Okay, good. Okay, clear.
Yes. This is what I did.
That's all from my side. Thank you.
Very good. Okay, so let's move on to the last part. Okay, so this is the inversion part. We have the problem is, or the problem statement is, we have a forward operator given by a differential equation, for example, Schrödinger equation, and it maps the feature space X, which is fixed for me, it's not uncertain. And then we have the parameters, which those are uncertain. And it maps it to some function space F. And then I have some measurements F. So the idea is to recover the parameters theta from a set of noisy observations Fn on a fixed grid. And this grid for me is a structured grid without any uncertainty. So the Bayesian inversion assumes that theta is random, right? It also assumes that we have the likelihood, the conditional distribution of data given the parameters. And then it uses the Bayes rule to update our knowledge about the parameters from prior to the posterior. Okay, the major challenge here is that the likelihood may not be available, especially in the case of quantum measurements. The noise, the uncertainty is so complicated that we don't have the likelihood. And this would increase the risk of likelihood misspecification, which again, in the context of quantum computing, this could have very severe consequences, which means this may lead to wrong gates, implementation of unstable or inaccurate gates. So the idea is to bypass the need for likelihood function. And for that reason, we use the generalized Bayesian framework or the Gibbsian framework. And that relies on having a loss function denoted by L. And then this would define a risk, an empirical risk function. And then the Gibbs posterior is defined by exponentiating a scaled version of this empirical risk times the prior measure. So this is not emerged from the Bayes rule. It's a result of a decision theoretic approach, which what it does is that it simply minimizes a cost function which measures fidelity to the data and fidelity to the prior. And it can be derived in just 3 lines. So given a prior and given an empirical risk, what we want to do, we want to find a posterior that minimizes a cost function split into 2 parts. The first part is fidelity to the data. So this is, we want to minimize the expectation of this empirical risk. And then also the fidelity to prior. And this is nothing but the Kullback-Leibler distance between posterior and prior. And then we scale it with this scaling parameter lambda. This is often referred to as the learning rate. Okay, all we need to do is we can factor pi here, write it in this form, and then we take derivative, equate the derivative equal to 0, and then we recover the Gibbsian posterior. So it's a general case of Bayesian posterior because with this particular type of empirical risk given as the sum of logarithm of this conditional distribution, then we can recover the likelihood function in Bayesian inversion. And for this reason, it's called a generalized Bayesian framework. The good thing is that it takes the form of the Bayesian posteriors, where this exponential function can be regarded as a pseudo likelihood. And the good thing about this is that this enables us to use very well developed techniques for computing Bayesian posteriors to compute Gibbsian posteriors. And I think that by now the idea is very clear. The idea is to use Sinkhorn distance as the empirical risk. Okay, the only thing is to, I mean, the data processing involves two steps. One is we first remove the zero frequency of the signals, and that is, I mean, the reason for that is a little bit technical. It's to make sure that the H dot inverse norm of the signal exists without removing zero frequency. We cannot bound the H dot -1 norm of the signal. And this is crucial for obtaining a very robust posterior. By robust, I mean stable against changes in the data and changes in the forward model. And then the statistical interpretation is straightforward. Instead of, so suppose that we have normalized the signal so that we have a positive unit with unit mass vector. Instead of the standard approach that we view this as a random vector in Bayesian inversion, what we do is that we view this as a discrete random vector that takes values xi's with probabilities being this normalized data. Okay, with this interpretation, one can use Sinkhorn distance and then the generalized Bayesian framework to obtain like a nice Gibbsian posterior for the parameters. And this would, of course, since it relies on Sinkhorn distance rather than Wasserstein distance, it, I mean, remarkably improves the Wasserstein derivative Bayesian inversion that we did a couple of years ago. One can do analysis. I will go through this very quickly. One can show that the Gibbs posterior is indeed a Radon probability measure. The only assumption is that we want the prior to be a Borel probability measure, and then we need the forward map to be a continuous map. And then one can show robustness in the Hellinger distance sense, the distance between the posteriors, the original posterior and the perturbed posterior can be bounded by the perturbations in the data and in the forward model. But instead of L2 norm, we can bound it in H dot -1 norm, which is much more robust compared to the L2 norm. And then one can also show consistency, meaning that as the number of data increases, if we have if we have proper conditions on the data and on the forward map, then it would learn more the parameters, the true parameters. Okay, this is one simple example. It's a 1D wave equation, super simple. I cook it so that I have the exact solution, and I synthesize the data. The data, so the uncertain parameters are the uncertain parameters in the initial condition. It's the phase and amplitude of the initial wave pulse. And then I cook it so that the the likelihood is actually Gaussian, right? So I have an additive Gaussian noise. This looks like a super simple example, right? I have just the one-dimensional wave equation, very simple setup. The noise is super simple, and I actually know the likelihood. So I make it two-dimensional by measuring the solution at a set of discrete points. So the vertical axis is time, the horizontal axis is x. This gives me a structured, the data, the noisy data on a fixed structured grid in 2 dimensions. Okay, and what I'm doing here on top, we have Bayesian posteriors. This is the profile of the likelihood versus the 2 parameters, and you see it has local minima. And the problem with this is that theta 1, so my true theta 1 is 0, and my true theta 2 is 5. I expect the posterior to get, to be around 0 for theta 1, but you see that it gets concentrated around 0.1, 0.5. And what is 0.5? 0.5 happens to be one of the local minima. So the Markov chain Monte Carlo sampling gets stuck in one of the local minima. And one needs to do many samples it would be much harder to avoid the local minima. While the Sinkhorn-Gibbsian posteriors, you see the profile is much more convex, and it gets concentrated around the true parameters. Application to quantum characterization. So we have applied this to real quantum measurements. And what you see here on the top, so the very top panel shows if you see the gray lines are simulated populations which are obtained by samples from the Bayesian posteriors. And you see, and then the colored curves are the true data. Here is for 2 types of measurements, the first and the third one obtained by Bayesian inversion. And what we see is that the posteriors fail to capture, they are first of all, they are biased, and they also fail to capture the uncertainty in the measurements. And the second and fourth panels show the same thing, but using this optimal transport or Sinkhorn-Gibbsian posteriors, which have a much better performance in capturing the uncertainty in the measurements. And this is
Mohammad?
Yes.
We're getting close to wrapping up time.
This is one, I will be done in 1 minute.
Great.
So this is the plot that I showed earlier, and the red curve that is like the gate infidelity in quantum computers is stable and robust, is obtained by the optimal transport driven Gibbsian posterior. So let me just make a few concluding remarks. Quantum computing has the potential to become the next computing technology. We have still a long way to go, and I strongly believe that mathematicians and statisticians, beside physicists, can play a major role in achieving the quantum advantage. Thank you.
Thank you very much, Mohammad, for this.